announcements because I got a bunch in the beginning of the term. Sometimes they come in flurries. So let me get a few of these noted. All right. A couple of campus organizations are getting up and running. One is the Scholars Bowl. I don't know if you've heard of this before. Mr. Matthew West, down in the sociology and history instructor, is the coach for the Scholars Bowl team. They're recruiting players for the 2019-2020 season. Scholars Bowl is a competition of questions and answers played with teams with buzzers. Questions are read, players buzz in without consulting, and if they think they know the answer, if they give the correct answer, they earn points plus a bonus question, which they then can work with their team to earn additional points. Questions cover a wide range of academic topics, mostly from science, literature, history, fine arts, geography, philosophy, and the social sciences, plus pop culture, sports, and current events. The Lawson State team practices every week and competes against other colleges about 2 to 3 times per semester. The first practice is day after tomorrow, beginning at 12 noon. And this will be down the half flight of stairs here in room 261. It's the middle classroom on the left between 259 and 263. That's Thursday at 12 noon. Now, you got to leave in an hour and 15 minutes to come to this class, okay? But other than that, you should be able to participate. All right. The flyer that goes with it, Scholars Bowl is currently recruiting players with knowledge in any subject, including history, literature, science, music, current events, mythology, and mathematics. They mentioned a couple others here. It's not quite like Jeopardy, but it's not too far off from that either. It's just in teams. There's another team that's forming up. They have at least 1 or 2 competitions a year, and that's the math team. And they meet, our first meeting that I know of is this Friday from 10 till 12, and this over on the Birmingham West campus, and this it's called the Science Building, room C103. Now, in addition to preparing for competitions, there also, Mr. Rossi does tutoring then as well. So if you'd like to go for tutoring, that's a good chance to do that. Another thing that's coming up, now the deadline isn't until October 16th, but this is the time to get started. The NCAS, there's a little sign back there that says that. That's the NASA Community College Aerospace Scholars, okay? NASA has this program going. You can participate, invite you to a 5-week online learning experience. While in the course, you learn about the history and future of NASA exploration, talk with NASA scientists, engineers, and complete a final project. Actually, 1 year they actually got to participate with one of the things that were going on out in space. They were participating in an experiment. They were performing out there on the space shuttle, on the space station. So all kinds of good things can happen with that. I have several websites you can go to check into that. Start the process if you're interested now. October 16th is the deadline. And then this came in the mail this morning. I don't know if any of you are interested in it. It sounds fun. Not at first, maybe. The Board of Governors of the Federal Reserve System, that was the letter. Okay, I went, what? Why am I getting this? Am I in trouble? But they have 2 programs going on. The first of these is the College Fed Challenge. Okay? It's a competition in which teams act as members of the Federal Open Market Committee and present their monetary policy recommendation to a panel of judges, and the finals are hosted by the Board of Governors of the Federal Reserve System, and team members get to meet Fed Chairman Jerome Powell. Okay? So pretty interesting there. Then The second of these is exploring careers in economics. The event offers students a chance to speak with research assistants, staff, and economists about the field generally, as well as career opportunities within the Federal Reserve System. And so there's this possibility as well. Welcome students and teachers in person and nationwide via webcast to discuss career opportunities, learn about career paths. They do it each spring and fall. Recording will be made available on demand, blah, blah, blah. So if you're interested in that as well, the information's up here. You're welcome to come and get it. Has anyone else come in since I called roll? Okay. All right, we're ready. I thought I turned on the projector, but it must not have taken. Okay. What's that?
You're getting to see now.
Oh, way past that. Okay, yeah. All right. Let's talk a little bit about what's coming up, especially today. Since last time we finished chapter 17, we're going to have the lab for 17 today, and I have spent, I had one little chunk of office hours this morning. I spent most of that trying to find a computer lab where we can have our lab today. I think I've got one for sure, and possibly a second one, but I think we'll probably go downstairs and do that. So we do have a lab today, so we'll only be in class from now until 3:15. At 3:15, we'll go downstairs and do the lab for chapter 17, and then we'll come back up here or stay down there, whichever you prefer, for the test. And the test will be on 17 as well. Okay, so hopefully you have your formula and equation sheets ready, right? All right, we're currently in chapter 18, so that's where we're going to get started today. Any questions first on 17 or anything else that we've done up till now? All right. What have we talked about as far as the structure of the Earth so far? What did we hit first? The crust. That thin little layer, only a few miles deep. It sounds pretty deep to me, but that's the crust. Very, very minor part, okay? But it's where we live. Next below the crust is the mantle. And you talk about a thick shell, it's this thick shell between the crust and the core. We'll see an illustration of this in a few minutes. The mantle takes up 80% of the Earth's volume. The crust, almost negligible volume. And here's, let's see. All right. Anyone else come in since I called it off? Okay. The crust takes up almost a negligible amount of volume, but the mantle, 80%. That's the biggest chunk of the Earth is in our mantle. It accounts for about 2/3 of the mass. This is 4/5 of the volume, but about 2/3 of the mass. That's because the core is really, really dense. Very, very dense. Okay? Now, the mantle is composed mainly of olivine, which is a ferromagnesium silicate. Very high in iron content, but it's still a silicate. Okay? Olivine. Now, anyone ever been down to the mantle? I really doubt it. Okay? I think the Soviet Union or Russia or somebody was trying to drill deep enough to get to the mantle. They may have succeeded, and there are places where the mantle is, the crust is very thin, so maybe we have been there, but mostly not. We get our data from three sources. The seismologic data that we started talking about before. Remember, what kind of seismological waves do we have? 3. They had very creative names, the first 2. What? Okay, in surface. Okay. Primary waves, called P waves. Another name for that is a pressure wave or compression wave. The secondary wave, secondary wave, that's another name for that is a, say again? Transverse wave, also called a shear wave, and that's secondary shear, transverse, okay, and then the surface waves are just those that form on the surface. Those are waves that come from deep in wherever the earthquakes were or are, and then when they come to the surface, they make the surface waves, which sometimes are the biggest waves, but they're not the most important. Now, this seems really bizarre, okay? How do we know about the mantle? The nature of meteorites. What? Meteorites are things up there in space that come down and hit the Earth, okay? How does that tell us anything about the mantle, okay? Derek's here, right? Okay. Now, it's a stretch, but some of the meteorites, remember from previous chapters, chapter 16, I believe it was, remember there were several kinds. There were iron meteorites, stony iron meteorites, and maybe another one or two. The iron meteorites are very similar, we think, to what the mantle is. Well, that's what formed most of the solar system. The meteorites are just the junk that was left over, so that's why they're fairly similar, we think. That's my best idea of the stretch they got there. And then, of course, the other data source is materials ejected by the volcanoes, because that's where it's coming from, the mantle. Okay? So that would be the other data source we have. Now, there's yet another correlation, they say. The basalts, and where do we usually find the basalts? Where are the basalts usually found? The ocean. The ocean crust are usually basalts. They are close to the silicates chemical composition of the stony meteorites. I would have thought the iron meteorites, but they're close to the chemical composition of the stony meteorites. Okay? And they're also the most common, the basalts are the most common volcanic rock, so their composition will not be far from what is in the mantle. Okay? Of course, the crystal structure may be different because the mantle is way down there, cooling very slowly, whereas the materials ejected from the volcanic rock is going to cool very quickly. However, rock come out of the volcanoes as well. So when you find the chunks of rock, that's probably chunks of the mantle that have broken loose and have come out. Okay? So that's the mantle. Any questions on the mantle? All right. Let's move even deeper. We're down in the core now. The core is made up of two parts. We'll get to that later. It makes up 15% of the Earth's volume. 15%. Now, how much was the percentage of the mantle? Anyone get that? Uh-oh, wrong way. Yeah, the mantle was 80. If the core is 15, what does that leave us with? 5% is the crust. That's not much, folks. 1/20th of the volume of the Earth is in the crust. Okay, 15% in the core, but 1/3 of the Earth's mass is in the core. Now, how much of the Earth's mass was in the mantle? 2/3. What does that leave for the crust? Negligible. Okay, it seems to be 0, but there is a little bit there. Of course, there's some there, but there's so much mass in the core and so much in the mantle. The crust mass is almost negligible compared to those. Okay, so well, that's 30% of the volume, 33% of the mass, That means it's really, really, really dense. And the mantle is even denser than the crust, so the crust is pretty low density. So, how do we know the core is down there? Okay? Here's partly. Remember, we keep talking about the seismographic data. Now we're going to see it. The P-wave seismologic data tell us a whole lot of information. The P-waves, remember what do they represent? Hit them one more time. P-waves. Primary waves. Pressure wave or compression. Longitudinal is another way to call it. Okay? Because they move in the same direction of the wave propagation that the matter does, these go through solids, liquids, and even gases. I'm speaking now, you're hearing me, I hope. That means that the sound wave, which is a pressure wave, is going through a gas even. So the P waves, now, when they're refracted, especially by the core, you produce a shadow zone. Okay? And here's what they mean here. If we have an earthquake here, now that's somewhere well below the surface, that it's not much out of the mantle, much out of the crust, barely into the mantle, but wherever it is that it's doing from, then they send out these primary waves in all directions. Okay? Now, those that stay in the mantle stay fairly close to each other. There's a little bit of diffraction there, but they go out. But then, when they reach the core, and whatever the boundary is there in the core, there's a great deal of refraction going on there, because you're going from pretty dense solid to an even denser liquid. Okay, we'll get to that part later. But there is refraction there. And actually, they get tighter as they go in and then start spreading again. Now, we'll talk about that later. That's mostly because the solid in the center is solid, and this around it, the outer core, is liquid. And that's what creates that change of concentration of the P waves. But what this results in, and when it comes out of the core again, there's another refraction or bending of the waves, and that leaves us with a shadow zone. When there is an earthquake on one side of the globe, they can measure it all the way down to 103 degrees away. That's more than 90 degrees away, but then there's a blank. From 103 to 142 degrees, no P waves are detected. And then all of a sudden, you start detecting the P waves from that same earthquake that you saw up here, you see down here. It takes a little bit longer to get there, but still gets there, but you see nothing in here. Nothing there. Now that's because of the refraction that goes on. That's refracting means bending by the core. It bends them inward and then lets them spread out again, but it leaves that shadow zone on either side. And this is all around the globe, is that shadow zone. You get them through all the way through on the other side, you get them near, but you have a shadow zone all the way around. And that's because of the increased bending or refraction of the waves in the core. That's how we know about how big the core is. That also contributes to how we know how massive, because the more they're bent, the more massive it is down there. Okay? So that contributes there. No direct P waves are seen between 103 degrees and 140 degrees of wherever the earthquake hit. Okay? That's used to calculate the shape and size of the core. They run models from the best data they've got about what's down there. That gives them the only model that fit, or the model that fits best is this one that gives us the shape and size that we just talked about. Okay? And these are used to calculate the shape and size of the core. The source of the data on the interior makeup of the core. Okay? Now that also, the fact that there is a solid core inside the liquid core, that's also contributes to the model that we have here. Okay. Now that's the primary ways. Tell me some characteristics of the primary ways. Not just what they are, but some of the characteristics. Fast, slow, middle, what? They're the fastest ways, okay? And they travel through solids, liquids, and gases. But there's not many gases down there, so we don't worry about that. But solids and liquids. How about secondary ways? Second, they do not travel through liquids. They are second fastest. They're faster than surface waves, but they're not as fast as primary waves, but they do not travel through liquids. And guess what happens? So here's, continuing with the core, the S-wave seismologic data show a larger S-wave shadow zone everywhere from 130, 103 all the way around the globe. Nothing gets through. It doesn't pick up again somewhere else. The core is acting like a liquid because the secondary waves cannot go through, not allowing S-wave propagation. So the core has to have, well, the core does have two parts. There's a liquid outer core, but then there's a solid inner core that brings those waves closer together again. That's supported by the S-wave and the P-wave data. So here's what the S-wave looks like. Now, I don't know if you can see it. If you got your books, you can see this. They made the S-wave look like little jiggles here. That's because they're, as Cameron said, transverse waves. They are shear waves. The motion of the particle is up and down, where the propagation of the wave is perpendicular to that. If they hit the core, they can't penetrate because they're transverse waves. Okay? They only get deflected by the core. So again, we get an idea of how big the outer core is, but we know no waves, S waves, make it through. P waves do down here, not here, but they do here. So that contraction of the P waves and then expansion again, that tells us that there has to be, or at least indicate, there's a solid inner core. Okay? But the outer core has to be liquid because the S wave will not penetrate it at all. So, interesting how seismologic data can give us information about what's going on inside. The seismological data was done by earthquakes, which happened inside the earth, but it tells us so much more than just it happened. It tells us a lot more. Okay. Did you get all that? Okay. Here's the other core evidence. And here we're back to the meteorites again. I'll tell you, I don't know. The iron meteorites, mostly iron or iron-nickel alloy, are thought to mimic the central composition of the core, because that's what was left over after the Earth and the other planets were formed. Those are the things that were left flying around out there, the rocks. So it sort of makes sense they would mimic this, and since we've studied them, we know basically what they are like. We think that's probably what the inner part of the Earth. The densities and the other characteristics of them seems to fit the models pretty well. Now, the other thing, I think we talked about this before, the Earth's magnetic field. Now, what is it that produces a magnetic field? Moving charge. Why would charges be moving? Well, certainly the Earth is spinning. But why would there be charges? Because the inner part of the mantle is probably a rough, jagged, uneven, rocky, hard material, whereas the outer core is liquid. So where those are bumping into each other and rubbing past each other, it's probably knocking off electrons. And then they're spinning in that gives us our magnetic field. The source is a turbulent flow within the liquid core. Turbulent means not just laminar flow, not straight flow, but flow that flows in eddies, okay, because they're being knocked around really quickly, okay? Material must conduct electricity, and let's see, what was the inner core? made mostly of iron, conducts electricity pretty nicely. So, the meteorite and the magnetic field data are consistent with an iron core. Makes sense. And that's what the meteorites are made of, iron, mostly. Now, I brought with me from the farm, we went to our farm over in Georgia this past weekend, and ever since we've lived on the farm, that was back when I was 4 years old, when we moved down there, we have been finding, and people before us found it too, chunks of really weird-looking, heavy, dense material lying around as rocks. The best guess from people we've sent it to and talked with about it is that possibly there was a fairly major meteorite hitting the Earth somewhere around that, and chunks of it around. I brought back a chunk this weekend. I was mowing under a fence, and there was this rock that I was afraid I was going to pick up with the mower, so I picked it up, and it was really dense. I said, let me take that to class. So I brought it. Well, not today's lab, but the next lab, we're going to be calculating density of certain materials. We're going to calculate the density of this and see how it compares. Okay? But these are consistent with an iron core. Now let's get a little more detail in the structure. Sure, we have a crust. Sure, we have a mantle. And sure, we have a core with an inner and outer core. But let's get a little more detail than that. Now, does anyone recall what the layer is just below the crust before you get to the mantle? It had a really long, strange name. It's called a discontinuity. I'll give you the last name. What's his first name? Shortened to be the MOHO. Mohorovicic, I guess is how you say it, discontinuity. That's the boundary between the crust, whether it's the oceanic crust or the continental crust, and the uppermost part of the mantle. That's the Mohorovicic discontinuity. Okay? You know that the speed of the seismic waves increases in the mantle, decreases when it gets to the crust. Okay? That's that discontinuity. Now, we're not going to talk too much about that, but just to remind you, that's still there. Okay? Now, then you hit the upper part of the mantle. Okay? They call it uppermost mantle here. And somewhere below that, there is a layer, and that's called the asthenosphere. Now, sphere means a three-dimensional circular object. So the asthenosphere is this layer that goes around. It's not a thin little boundary. It is actually a layer. It's in the upper part, or just below the upper part of the mantle. It's a thin, compared to the rest of the mantle, hot, elastic. Now, what do we mean by elastic? Elastic means it returns to its original shape when deformed. Okay? Elastic, but semi-liquid. So those two things don't seem like they fit together well. Semi-liquid layer that's in the upper part of the mantle. Okay? It's distinguished by a sharp decrease in the seismic wave velocity. Okay? So it's going through the upper mantle pretty fast, but then it hits this liquid, which semi-liquid, not total liquid, elastic, so it does go through, and the S waves go through, so you know it's not a solid, not a liquid totally. The S waves go through, and it's sort of thin, so they make their way through. But the speed, the velocity decreases when you go through it, then picks up again when you're out of it again. So that's there. It's called the asthenosphere. Now, talking about spheres, remember in the last chapter what I said litho stood for? Back when we were doing sedimentary rocks, the rock forming process, litho, but that's where we ran into litho before. Now we're talking about lithosphere. What the lithosphere is the crust, including the Mohorovičić, okay, the upper mantle, everything above the asthenosphere. And it's all solid above there, except for the ocean, of course, we don't count that. But it's all solid above the asthenosphere, but the asthenosphere is semi-liquid, okay? Now, the lithosphere includes the entire crust, everything in the crust, continental crust, oceanic crust, everything in the crust, the moho, the discontinuity we have there, and the upper part of the mantle. That's all what they call the lithosphere. It's where the rocks are, okay? Now, this is where we transition to the next chapter, okay? Well, actually, no, this is the foundation of this chapter. Plate tectonics. I was in the wrong chapter, okay? This is what makes plate tectonics work. It's made up of rigid plates that float in the upper mantle. What are they floating on? The asthenosphere, okay? They're not like the lower part of the mantle. That's pretty much solid, okay? The upper part of the mantle above the asthenosphere, that's what's in the plates. The whole lithosphere, because the crust are with the upper part of the mantle. So everything in the lithosphere are made up of these rigid plates floating in the upper mantle on top of the asthenosphere. That's what makes plate tectonics work. And that's why we're finally getting there. Had to get all this other stuff done before we got there. Okay? And then you see here the outer core, which is liquid, inner core, which is solid. And most of the mantle is down here, solid. Then you have the asthenosphere, and then the upper part are plates that are rigid plates floating on that asthenosphere, the upper part of the mantle. All right, and that's where the theory of plate tectonics gets its basis. The individual continents shift positions on the Earth's surface. Okay? Now, some of the continents are together, like Eurasia, Europe and Asia. There's no split there. And not all the continents are together. India is part of Asia, we say, but it's actually part of a different plate. The patterns between the continental shapes can be fit together. Now, this was the early theory that preceded the plate tectonics theory. It was called continental drift. No one could imagine why it happened. It just looked like it was happening. Okay? And if you look at the map here, there's so many things that are so bizarre. Now, this is the Atlantic side of things. See how Europe kind of tilts over that way, but the U.S. tilts the other way. I mean, tilts so it fits. Okay? This chunk of Africa here almost could go into the Gulf of Mexico, Caribbean Sea here. And notice how Brazil, how it humps out in South America here, that fits almost perfectly in the armpit of Africa. Okay? Everything seems to fit. And if indeed that was the case, then that original huge, massive continent was called Pangaea. Pan meaning everything. And when you have a disease outbreak, if it's really severe, what do they call it? Okay. The first layer is epidemic, meaning there's lots of it. But then when it covers everybody, it's called a pandemic. So you're absolutely right. The pandemic is everything. So this is everything. And Gea, that's the same root word for geology. You know, the Earth's surface, the Earth's crust was all together one big continent. Okay? But then it sort of breaking up is hard to do, you know. So things started breaking up and spreading apart. And that's what we think happened here in the Atlantic. You can almost see there's a sort of crooked line that goes through there that would indicate where the split occurred. Originally, they called it continental drift just because it looked like it would have happened. And they thought they could measure things that indicated they were getting a little further apart. Now that we have plate tectonics, yeah, we can explain it a lot better. Now, evidence from the Earth's magnetic field. Now, there's something here that I can't even begin to fathom why. I can have a few ideas, but that's about all. What are igneous rocks? Yes, rocks that were one time molten. So igneous rocks can record the Earth's magnetic field strength and direction. Now, all the time that man has lived on the planet, now, this is not going to be very scientific or precise, but I hope it'll give you an idea of what's going on here. If you count the formation of the Earth to be this corner down here, okay, that was the timeline for the formation of the Earth. And this corner here is going to be the present, right now, okay? And you split all that history of the Earth along that timeline, okay? Mankind has been here probably right about here, okay? We weren't here, there, or there, or there. We were only showed up very, very, very recently. And as long as we've been here, that anyone knew anything about it, compasses point toward the North Star, toward the North Pole. But when they dig down into the Earth, okay, anyone ever heard the term lodestone? Lodestone is naturally occurring iron that's magnetic. There's only three naturally occurring magnetic materials: iron, nickel, and cobalt. And if you find the periodic table, it should be somewhere in your back of your book. Here's iron, Fe, cobalt's right next to it, nickel's right next to cobalt. Three right there together. They're the only three naturally occurring magnetic materials. That's all, folks. Aluminum, no. Copper, no. Nothing else is magnetic except those three. Well, most of the Earth's core is iron, right? So when we have volcanic eruptions, if things spill out, you get layers of iron. Now, sometimes those layers of iron line themselves up with the Earth's natural magnetic field. And if that molten material lines up with a strong magnetic field, then that's magnetic. And that's where naturally occurring magnetite is the mineral, just like hematite, except it's magnetic and hematite isn't. And so you get layers of that. Okay? Sort of makes sense, right? Strong Earth magnetic field, the liquid forms, lines up with that, and forms naturally occurring magnets. So that's what we're talking about here. Igneous rock records the magnetic field strength and direction. Magnetite poles are locked into alignment with the Earth's field on crystallization. So you have naturally occurring magnets. Okay? Now, you go through layers of this, and sometimes you'll find iron that is very strongly magnetic, and then iron, you go through layers that have weaker magnetic fields, and then no magnetic fields. And then here's the strange thing. The Earth's magnetic field varies in not just strength, but in direction over time. In the they've measured 22 reversals over the past 4.5 million years. Okay? Now, 4.5 million years might be somewhere about here, okay, in that timeline. Because that's, remember, in the billions from there to here, so 4.5 million is just way over here somewhere. We are right in here somewhere, okay? We're still in the last reversal of thing. It hasn't reversed since we've been around, but they've registered 22 reversals in the past 4.5 million years. Now, for the life of me, I can't figure out how in the world that could reverse. Because you would think if charges making a magnetic field, either the Earth would have changed the direction of its spin, which is no indication it's done that, or something else is going on, and I don't know what it could be. Now, my best supposition, and I have no basis for it at all, but it seems like just about everything in nature follows cycles. If you haven't noticed that already, just about every chapter has something on cyclic material, so activity. Well, if you think about a magnetic field, it might be very strong, weak, reversing, strong, weak, reversing, strong, weak, reversing. Just about everything follows these sinusoidal patterns called harmonic motion, harmonic activity, okay? And if indeed something about the way the spinning is going on in that inner core, if there's a little bit of a precession with that, within our precession a little bit more, then it could be that it's turning over in time. Why? I don't know. Okay, I can't even begin to guess, but it could be, and that would be why it would vary in strength. Sometimes it's very strong here and here, and sometimes in here it's very weak. And they measured this by taking cores and see layers of iron with no magnetism, and then they get more that are really strong. So here they're really strong, but in their opposite directions. So that would fit if that's the kind of activity that's going on. I can't tell you why that would, but it seems like that would work. 22 reversals over the past 4.5 billion years. And it seems to be, some of the things I've read, that we're sort of getting weaker now. So we may be entering a phase where we're going to not have much of a magnetic field. And then what will we do for compasses? Well, hopefully we have gyroscopes and stuff like this. We won't need them. Although I think you said in the Navy now they don't shoot the stars anymore. They don't need to. Okay. But they used to. Okay. So maybe we won't need it. But then sometime later you'll be compass needles pointing in the opposite direction. Well, then we'll just turn the arrows around and make them point back. So we won't know. Okay. All at the same time we're precession. That's going on. So here's the pictorial diagram of this. If the direction of the Earth's magnetic field is like this, and believe it or not, it really is. Okay. Here's my good old handy dandy visual aid. Always hard to find. Right there is magnetic North Pole. Not quite the same as our true north, but right there. Magnetic South Pole. It's even harder to find. There it is. Drop the blue. There it is. Okay? So they're not lined up with the North or South Pole. The South Pole is way off, but North Pole is much closer. Okay? Now, if we were standing here, I am anyway, in Bessemer, Alabama, and if I told you point to north, your best guess of where the North Pole is. Any of you have an idea? Yeah, okay. Yeah, something maybe about like this. I think I'm about right, something like this. But you know where I'm pointing? If I'm standing here, I'm pointing out into space here. I mean, this way. But I'm pointing out into space. Because I'm on the surface of the Earth, I point this way, I'm pointing out into space. If I really want to point toward the North Pole, it's down there somewhere. Because the Earth's a sphere, I have to point toward the North Pole. And that's here from where I am, so I have to point slightly downhill. That's why these are not just pointing north and south, they're pointing down at an angle. Okay? Now, right on the equator, that would be almost horizontal. Most of it's not. So magnetite crystals preserve the orientation of the Earth's magnetic field. So this upper layer of those magnetite crystals are here, and let's just say this next layer was a little stronger, but then you got weak again, and then suddenly you hit a layer. Well, you may have some layers that there were hardly any direction, but the next layer is pointing this way, meaning that the poles have flipped. And that makes no sense unless, of course, you're doing this kind of motion and you're just seeing this one and this one with almost nothing in between, or very weak in between. So sure enough, they've measured, as they've gone down in cores, they've measured 22 of these reversals as you keep going down, 4.5 million years into the past. Bizarre, but true. Now, let's consider some evidence from the ocean. Now, we're talking Atlantic Ocean here, not Pacific. Atlantic Ocean. Okay. Now, but there's other places on the planet that have them too. So the major one we're talking about now is in the Atlantic. You have these oceanic ridges. Just out in the middle of the ocean, suddenly you have a ridge there. Well, you know that's happening in the Pacific because everywhere you see an island out here, you know that it's a mountain on the bottom of the ocean, but it just gets the very tip of it to break the surface because the ocean is really, really deep out there. Okay, the tallest mountains in the world are in the ocean. They're not in the Himalayas. Okay, they're really tall mountains there. Okay, but anyway, but here in the Atlantic, just going down the middle of the Atlantic, there is this ridge. Deep on either side, but not as deep in the middle. Oceanic ridges. And these coincide with submarine, meaning beneath the water, submarine, beneath the water earthquakes. Okay? There's a rift along the crest of those ridges. Large amounts of heat escapes from that crest, meaning volcanic activity is right there in those crests. Okay? This is called the Mid-Atlantic Ridge. Let's see if we can get a picture of it here. Okay, there it is. And here's an island right in the middle of it. Iceland. Okay. Iceland is a volcanic island, or actually a chain of islands, but the major islands, they're all volcanic islands. You would think as far north as that is, okay, here's England, that's pretty far north. Here's Norway, Sweden, those are pretty far north. Iceland's even further. Up there along with much of Greenland here. I guess we're going to buy it this week. No, probably not. Okay. But anyway, it's way up there. So it's really, really cold, right? Or it should be. And it is. Except, you know, they probably pay less for cooling than we do, for heating than we do. Because they're in a volcanic island. Right beneath them is magma. Okay? Well, it's magma. Hot, liquid rock. What they do, they drill down into it very carefully and pump water down there, and then the water heats up and comes back up, and they take that and they pipe it through their streets into people's homes. They hardly have to pay any electrical heating at all. They warm their whole population pretty much with geothermal heat because they're right there on an island. There, the islands have actually crested, broken through the surface. That's what Iceland is. And all along this ridge. Now, an earlier edition of the book had a video with it, and I can't access that anymore, or if I can, I don't know how. But it came on a set of CDs, and I could plug those in. They won't work anymore, because they're not using that edition of the book anymore. And you could see they had underwater cameras down there all along some portion of this ridge taking pictures. And you just see the lava bubbling up in the middle of the ocean, just flowing out on either side of that ridge, the Mid-Atlantic Ridge. Okay? That's what that is. Now, there are also oceanic trenches long, narrow, but very deep troughs with steep sides, and these are always run parallel to continental edges. Okay? Not so much in the Atlantic, but on the Pacific side of things. Okay? When I was in the Navy, my home port was Concord, California, which there wasn't much there. We were an ammunition ship, and the original weapon station there was Port Chicago on, I think, the Sacramento River. But during World War II, a commercial ammunition ship that was carrying weapons to the Pacific, I guess, to fight the Japanese, they had an accident. Something blew up. It wiped out the ship, the town, everything around it. It was just a level, flat, almost as far as the eye could see. So there is no town there anymore. The closest town is Concord, which is a good deal inland from that. We didn't spend much time at Port Chicago. We loaded and unloaded there, but other than that, we went somewhere else. So we were always near San Francisco area. And when you would go out, pass under the Golden Gate Bridge, and go out into the Pacific, if you were watching your depth finder, you might say, that was pinging, then just whoop. I mean, it went way deep, and then it started coming up again. There was this trench that was all along the West Coast, and it goes down here. It's all along pretty much the rims of the Pacific. That's what they're talking about. Long, narrow, very deep troughs, steep sides, running parallel to the continental edges. And then once you get out there a ways, the bottom comes back up. Not near the surface, but it does come back up. So very, very deep right along the outside of the continent. Okay? That indicates a continental boundary. Okay. So here is the hypothesis for what's happening and why we have plate tectonics. Does anyone know what? Let's move to the Pacific. What the Pacific outline here is sometimes called. Johnny Cash sang a song, but he wasn't talking about this. The Ring of Fire, exactly. Okay? Because lots of things all along here are very volcanic in nature. The whole island chain of Japan, volcanic islands. The Aleutian Islands, volcanic islands. The Kuril Islands, volcanic islands. Most of our volcanoes are along the west coast here. You can just pick up names of them. Mount Katmai, Mount St. Helens, going blank on some of them, but Shasta. There's just a bunch of volcanic islands. You keep on going down South America, Chile. There's a ridge here of volcanic mountains here, okay? Just all along here. Then you have little island chains here, but actually New Zealand is a volcanic island chain. A lot of Malaysia and Indonesia, volcanic island chains. The Philippines, volcanic islands. They're just all over the place. That's the Ring of Fire. That's where most of the volcanic activity on the planet is along there. That comes from that. The hot molten rock moves up. Now, that's in the Pacific. What's happening in the Atlantic that's making that happen? Well, that's where hot molten rock moves up from the Earth's interior, emerging along that rift, the Mid-Atlantic Ridge. The outflow is in both directions, making new rock on both sides of the ridge. Always making new rock. It bubbles up, spills over, bubbles up and spills over. Just keeps doing that. Okay? Outflow on both sides creates new rock. The drilling evidence, and they've done drilling on both sides, there's thin sediment layers, not sedimentary, but sediment layers, near the ridge, becoming thicker as you move toward the continents, and becoming deeper as you move toward the continents, older as you move toward the continents. The older fossils and rocks near the continents become younger when you get near the rifts. Okay? Because that's all new stuff. Way down there would be the continuation of this one, but the new stuff is formed on top of it. Okay? Now these next few graphics here, I find not quite satisfactory to me, but they're okay. If you're looking just at the surface that you see here, this green in the middle, those are 0 to 5 million year thick things. I mean, the rocks and the captured animal life and stuff like that in that molten stuff, all new stuff. 0 to 5 million years. You call that new. I feel younger now. Okay. Then, on either side of that, you find stuff that's 5 to 23 million years old. Still fairly young. And then on the either side of that, this other shade of green here, that's 23 to 38 million years. And then the blue on the either side of that, that's 38 to 53 million years. And then the brownish that's on either side of that's 53 to 65 million years. And then the yellow, as you're getting closer to the continents, that's 65 to 135 million year old stuff there. So the new stuff's in the middle, pushing the older stuff further and further out. Well, somewhere back there, this was the new stuff, and it was closer. That's when the continents were closer together. Okay? But the new ridge is pushing away. Okay? Well, where's it going? Is the Earth getting any bigger? No. So what has to be happening over in the Pacific? Crust must be moving underneath. Because this is spreading out, you must be. The Pacific, believe it or not, is shrinking ever so slightly, because the Atlantic's not growing all that fast either. But that's what's happening. And that's why you get those deep ridges against the continent, because the oceanic crust is going underneath the continental crust. That's what creates those trenches. Okay. Sort of makes sense. Okay. Now, let's go back to our magnetic seafloor spreading evidence. In other words, we've got these layers of magnetic layers where they've been changing direction 22 times over the last, how many million years? 4.5 million years, something like that. The paleomagnetic patterns, that's the ancient magnetic patterns of magnetic strips and ocean floor in the basaltic rocks there, you've got them there, okay? Depending on where you are, you can count down to 22 reversals. The identical magnetic reversal patterns are on both sides of the ridge. You get closer to the ridge, you have fewer. You get further away, you get more, and they're identical as you go out from either side of the ridge. Close in and far out till you get to the continents out there, and they're almost identical there. Okay? So there's identical magnetic reversal patterns on both sides of the ridge. The patterns match those found elsewhere, providing age determination. So they do a lot of different things to determine age. They measure the carbon content of some of the fossils that are there. Carbon dating, they call that. It's sort of like makers.com. No, it's a different kind of dating service. Okay. Carbon dating, and they determine the age. But also these layers, they know when they occurred because they see it all over the globe. So they have a pretty good idea of when. That's what gave them those years they put in there. Now, this is the figure I don't really care for that much. Part of it seems to be pretty true, but another part of it is less satisfying, okay? They're showing the layers being vertical here, whereas the layers are more horizontal because the magma's coming up and spilling over, you know. But what they're getting at is the spreading effect. So that's what they're indicating here. You first had a little spread there. Well, that got spread by another spread, and those little spread got split on either side. then another one came in and split that a little more, then another one came in and split all those a little more. That's what they're getting at, but you see, the layers are more horizontal, they're not vertical like this. So that's the thing that sort of gripes me about this illustration. But it's showing the spreading. That's what the intention here is. Okay? I don't care for the graphic that much, but that's the intent. Okay. So we've got our measurements, our evidence. The stuff seems to be there. So this forms the basis for our plate tectonics theory. The lithosphere, tell me what the lithosphere is again. What component makes up the lithosphere? Little thin. Outer, what you call that, where we live? Crust. And what's right beneath the crust? That strange sounding MOHO, the MOHO discontinuity. And then right below that is the upper mantle. This is the fireplace here. The upper mantle. That's the lithosphere. Everything above the, what's the sphere below the lithosphere? Not that far. Don't go that far. Then elastic semi-liquid layer. Asthenosphere, the asthenosphere. Everything above the asthenosphere is the lithosphere. It's the upper part of the mantle and the crust and the MOHO. Okay? The lithosphere is broken into fairly rigid plates. Not totally. There are some cracks and crevices in those too. But the plates move on the asthenosphere. They float on it, basically. Okay? Earthquakes, volcanoes, and other rapid changes in the Earth's crust occur most often at the plate edges, where the plates either are splitting, running into each other, running past each other. That's where your hang-ups are. That's where your earthquakes happen. That's where the volcanic material comes up. They take advantage of the cracks there, and the stuff comes spewing out. Other rapid changes. That occurs often at the plate edges. Not always, but often. There are three plate motions. One in the Atlantic is divergent, moving apart. In portions of the Pacific, Indian plate and stuff like this, they're convergent. They're bumping into each other. And the last is when they're moving past each other, and that's called transform. So you have divergent, moving apart, convergent, crushing together, transform, sliding past. Sliding is not the best word for it, okay? We'll get to that in a minute. A few minutes. Okay. Here, we saw this in the very beginning. These are the predominant plates as we understand them now. Here's where we are in the North American plate. Now, there's mostly North America here, but our plate extends halfway across the Atlantic, approximately. North Atlantic, anyway. Just below us down here is the Caribbean plate, which involves most of Central America and a lot of the islands there of the Caribbean plate. Okay? Gulf of Mexico is above that. We're still in the North American plate there. Okay? On the west side of the North American plate, there's a tiny little plate here called the Juan de Fuca plate. I mean, it's a little sliver to be called a plate. And it kind of slides around there some too. And then beyond it is the Pacific plate, big old plate, almost all underwater, except for a few island chains and stuff that have come up where there's creases or cracks in it. Let's move on down here. There's the South American plate, which again, the western boundary is the boundary of South America, but the eastern boundary is the Mid-Atlantic, South Atlantic, the Mid-Atlantic ridge there. That's the other edge of it. Now, just below that, whereas we have the little Juan de Fuca up here, they have a pretty big plate down there called the Nazca plate. And one of the most interesting structures to me in the Nazca plate, or somewhere right in this boundary here, is Galapagos Islands. Now, I don't know if they're really part of the plate activities and stuff, but I would love to go there one day because that's ancient, almost untouched by man, fauna and flora that you don't see anywhere else. And my goodness, if I don't have a niece who was doing a geography study for her master's, and she got to go to Galapagos a time or two, maybe even 3 or 4, just to study the stuff there, and I was eating my heart out wishing I could get down there too. Now, here's the part, I think I mentioned it before. I don't know what this green blob is down here. They make it seem like it's a different plate, but they don't give a name to it. And it's far bigger than the Juan de Fuca, so why doesn't it have a name?
Do you think it's part of the little green or
It's colored the same as the Africa plate over here, which is this is the other part of that, but it's not connected to it. So, I mean, if it's not connected, it's got to be a different plate. So, I don't know. I wondered the same thing, too. There's the Africa plate, which is the eastern part of South Atlantic, and then the northern part of the Atlantic, that's in the Eurasian plate, the western part of the Eurasian plate. See, that's all under there. Pacific plate is all underwater. There is no Atlantic plate, okay? South American plate, North American plate, African plate, and Eurasian plate. That takes up most of your Atlantic Ocean because that was all one Pangea before, you know. The water just filled in between, but the plate boundaries are there. Okay. Interesting here, to me, is there's another huge, pretty good sized plate here that is the India-Australian plate. Who would have thought that India, which is part of Asia, was not part of the Eurasian plate, but part of the India-Australian plate. And most of the Indian Ocean is there, not all of it. There's a ridge there too, something going on there, and it curves up here. As I mentioned, much of Malaysia and Indonesia here are boundaries between these two plates. Philippine plate here, not huge, but good size. And you see, just like these colors seem to be the same, but that's a separate plate. I think that has to be a separate plate. Now the Antarctic plate down here, it looks huge, doesn't it? But you realize you got, that's what it is. You know, it's just a little bit down here, but when you spread that out on the thing, it makes it look like it's huge because you're trying to spread out a little part of a sphere onto a long part of a piece of paper. Okay. A lot of interesting things going on here. Here is the Arabian plate here. Almost all of Saudi Arabia is on one plate, and the Persian Gulf and other things are boundaries of it up here. Okay. So those are the basic outlines of your plate tectonics, the plates that make up that theory. So let's look at the 3 boundaries separately now. The first of these is divergent boundaries. It occurs between 2 plates moving away from each other. Okay? Now, it doesn't happen rapidly. It happens very, very slowly. But when they do move away, that creates a weakness in the crust, or the upper part, so magma can come up, okay, from deep below. Molten material from the mantle rises to fill the fissures between those plates that have moved apart. You get new crust being formed, mostly iron crust. It's the bottom of the ocean, so what kind of rock is being formed there? Second? Basalt, exactly. Your basaltic rock is being formed there. New crust zone happening there. Often accompanied by volcanic activity. Think the island of Iceland. In fact, it wasn't too many years ago, I'm going to guess between 7 and 10 years ago, Iceland had such a major volcanic eruption that it shut down airports because of the predominant winds up here, shut down airports all over Northern Europe. London, Heathrow was down for several days. Paris was down. Charles de Gaulle was down. I'm sure the ones over here in Norway and Sweden were down. Just all Northern Europe had to shut down all their air service because there was so much volcanic grit in the air. Jet engines don't do well when they suck in grit. They want to be sucking in pure air. When they suck in grit, the jet engines get destroyed. Okay? So that's where volcanic activity. Now, where's most of that volcanic activity? Under the water. You don't see it. You don't realize it. If you had a way of measuring temperatures, you would detect right down that mid-Atlantic ridge, you would find lots of heat activity going on from that volcanic activity. That's the prime example of a divergent boundary, the mid-Atlantic ridge. There are others across the globe that we will see in the last chapter when we study the oceans. We'll see other divergent boundaries. But that's the major one we're looking at now. Okay? Here's basically what's going on with that. Oh, man. All right. Now, I'm just giving you my best take on this. Okay? Here is the crust, and this is all underneath the ocean, so this is oceanic crust, which is relatively thin, mostly basalt. Okay? Underneath that, here is the the Mohorovic discontinuity, and then you have the upper part of the mantle. Okay, but the asthenosphere, which is that semi-liquid, elastic, hot materials down here, that is really close to the surface here. And that's what pours the lava into the fissures when you have these divergent boundaries happening. So that's the general picture here. It's nothing as pretty as this. These are very rough edges here, irregular, not smooth like this, and it's not all magma. It's a mess, okay? But you get new crust being formed on either side. And that's probably how this crust was formed. So there's that's the closest. You still are, well, yeah. The mantle is probably about as close as it ever gets here. If you wouldn't dive down and get anywhere near that, you'd be killed. Okay. So I was going to say you might get close to the mantle. Nah, you'd be dead. Okay. Now let's do the convergent boundaries. Now this is the opposite. Okay. And on these convergent boundaries occur when the two plates are moving toward each other. Not going to happen in the Atlantic. Those are moving away. So you go to the other side of the world. Those are some places closer to the Atlantic that it can happen. Two plates moving toward each other. Okay. Three situations here. We'll get to that in a minute. The old crust has to be destroyed. Okay. Something has to happen. They're crashing into each other. Something's got to give here. Some of the old crust has to be destroyed. What happens there, in at least two of the three cases here, is what we call a subduction zone. That's what's happening in the Pacific. Like I said, leaving San Francisco, you have the continental crust of the North Atlantic plate up here, the Pacific crust down here, which is oceanic crust. And because it's denser and thinner, and this one's thick, it gets pushed down underneath the continental crust. That's what we mean the old crust is destroyed. Mostly the oceanic crust gets subducted, meaning put underneath the other. There's a belt with one crust subducting under another crust. The subducted material gets pushed down, and at some point gets so hot it remelts, and then it goes back into the asthenosphere. Okay, creating new material to come up somewhere else. Okay, the subducted material that was crust goes back into being mantle now, and it partially melts and joins the mantle. There's three possibilities for these convergent boundaries. What I've been describing is converging continental crust with the oceanic crust. Continental goes above, oceanic goes below, the oceanic denser, so it goes underneath, continental rises above, but it creates problems. Wherever that's happening, those are not smooth, well-lubricated crust movements. They are jagged, ragged, irregular movements, and they get hung up on things, and pressure builds, until suddenly something gives way, and what do we have there? Earthquake. Okay, we'll get into that in the next chapter. Okay, that's happening here, converging continental and oceanic crust. Now, also out in the middle of the ocean, you have this going on. Now it's an oceanic plates are converging. Okay, and one of them either is lower to begin with or denser to begin with. It subducts under another. Okay, so that's the converging oceanic plates, not continental and oceanic. But here is where some real problems occur. When they're continental plate, when they converge, where are they to go? None. They don't subduct very well at all. So guess what they do? They grow. They crush into each other and get taller. Can anyone guess what mountains might be growing? They're already the big boys on the block, the Himalayas. Tallest mountains on the planet. But they are, look at there, there's India, the top part of the India-Australian plate, crashing into the Eurasian plate up here. That's why the Himalayas are there, because that's the place where continental are doing. They are actually growing. The Himalayan mountains are getting a little taller all the time, and you hear of volcanic activity along there pretty frequently. Sometimes in China, sometimes in other places. It's pretty brutal. Now, in the U.S., the Rocky Mountains are growing. And that's mostly because of, we'll get to this in a later chapter, the Andes down here are growing. Okay? These are growing. The Appalachians over here, they're getting smaller. They're probably way older than any of those other mountains. They one time were the kings of the hills, probably, but they've been eroding away, getting shorter. The others are getting bigger. Okay, that has nothing to do with this, but the growing mountains are basically evidence of converging continental plates. Okay, so let's look at each one of those separately. The ocean continent plates, convergence. This is the oceanic plate of the denser basaltic material subducted under the less dense granite-type material of the continental shelves, and that's what's going on there. Marked by oceanic trench, like I said, that deep trench goes past San Francisco, and all along that west coast of the Americas, you'll find that. Deep-seated earthquakes and volcanic mountains occur. Mount Rainier, that was the one I couldn't think of the name before. Mount Shasta. There's just a whole string of volcanic mountains here because of the Pacific plate subducting under the continental plate of North America, and that's what forms this ridge of volcanic mountains. What forms the ridge of the Japanese island chain. The oceanic crust is subducting underneath the Eurasian crust and Eurasian plates, and all this activity is going on. These are marked by oceanic trench, deep-seated earthquakes, volcanic mountains. Examples, the convergence of South American plate with the Nazca plate. That forms mostly the Andes Mountains here. And those are really tall, much more so than our Sierra Nevadas and the Rockies. They're tall mountains, but goodness, put your hand over that. These are distinctly tall. The Nazca plate here is subducting under the South American plate, and lots of volcanic activity there. Chile is famous or infamous for its volcanic activity because so much is going on there. Chile's building structures have been great for long periods of time because they've had so many earthquakes to put up with volcanic activity. Their buildings are, their codes are very, very strict. Fact, right around Christmas, close to a decade ago, I guess it was, they had a really major earthquake in Haiti. Okay. Huh? What's that?
Was it at Christmas time?
I'm sorry.
I didn't remember Christmas. It was at Christmas time?
Yeah, right around Christmas time. Right around in Haiti. And just about, and it was right Port-au-Prince, the most populated area, massive destruction. Houses, apartments, hospitals, everything just went tumbling down. Within a month or two of that, there was a earthquake in Chile. That, it was a pretty major earthquake, but the amount of damage was fairly minimal, which was the stronger quake. Chile, they had such rigid building codes, they were ready for theirs. Haiti hadn't experienced that. Haiti doesn't experience many earthquakes. We don't have many earthquakes in the eastern part of the Americas. They just don't happen. It happened in Haiti, and they had terrible building codes. And so the destruction was rampant, but it was a much weaker quake than the one in Chile, which had almost, they had some major damage, but not anything as much as Chile had. And they were only like months apart. So here's what's happening there. You can picture this as being the Nazca plate here and South America plate here. You can picture this the Pacific plate here, the North American plate there, whatever you want to imagine. But you see the oceanic lithosphere is being subducted under the granitic continental lithosphere here. And when that occurs, it's not a pretty picture. It's grinding, it's hanging up on rocks and boulders and stuff, and then there's a lot of heat being produced. They're melting their own rock, or they are creating fissures that the asthenosphere can come up and crawl along those fissures and go, and that's why the volcanoes form. That's why the earthquakes form here. That's sliding past. Whatever is opening up in the Atlantic has to be closing in the Pacific. And wherever that's happening, volcanic activity, major earthquakes, the ring of fire around that. Okay? These are shallow earthquakes when they're here, deep-seated earthquakes when they're down here. We'll talk about those in the next chapter. Volcanic activity, when some of that magma, some of that breaking and earthquaking and stuff like this happening, makes little breaks in the crust, then magma finds its way up and you have volcanic activity. It's happening really constantly. You don't always see the earthquake, feel the earthquake, but the tension is there, and when there's not been an earthquake lately, you know it's going to happen and it's going to be bigger. That's the one in San Francisco. This would have been probably 25 to 30 years ago. There was a World Series between Oakland Athletics and the San Francisco Giants. They called it the Bay Bridge Series. And during that series, really major earthquake happened in the Bay Area. And the Bay Bridge main thoroughfare that goes between, not the Golden Gate, but the Bay Bridge that went between Oakland and San Francisco, one of those lanes collapsed on the other one. There was lots of death and destruction there. It was a pretty messy situation. Okay, so that's happening out there. And then within a few months, Los Angeles had one too. So they didn't have as major destruction, but they had overpasses falling down on the highways. You know, it was pretty bad. Okay. Ocean continental plate convergence. Ocean plate convergence, that's the trench and the underwater ridge are created by subduction. Okay. The problem is they're both underwater. Okay, and you don't know who's winning or losing. These are associated with really deep-seated volcanoes because they're already pretty far down, and then they're going to be. And that's why you have these island arcs. That's where the melted subductive material rises up and finally breaks through sea level. And just look at the Pacific. I've mentioned a few before. The Hawaiian Islands are here they are. Okay, those are island arcs on the sea. The Aleutian Islands, very definitely an island arc. The Kurile Islands are Kurile Islands here, an island arc. That's part of Japan, an island arc. The Philippines, an island arc. New Zealand, an island arc. Much of Indonesia, Malaysia. This is Indonesia over here, Malaysia over here. These follow arcs. You have the Line Islands, the French. They're all over the place here. Little ones. Here's the Micronesia, that's an island arc. They're just all over the place out there, and that is formed when the subductive material rises up through the sea level, through the overriding plates. The plate on top, the one underneath, that creates the friction, creates the fissures, and then the volcanic activity happens. Most of it underwater we don't even realize. It's only when it breaks the surface that we say, "Oh, there's an island's forming here." Okay, and they usually are in those arcs because they're the edges of the plates. Okay, all this, remember, is underwater, but the oceanic trench that subducts under the other oceanic trench, then all the friction that happens here when it gets down into the magma, into the mantle, the friction hits in, breaks into the the asthenosphere, and that liquid comes up. Finally, they break the surface, but those have been forming for years. Okay, it's just when they break the surface we start seeing the edge of that. Here is the trench down here. That is deep. The deepest part of the ocean on the planet is here are the Marshall Islands. I know they're on here somewhere. I've got to find them. There they are, the Marianas Islands. See, if you look carefully, there's a little arc of islands, and just on the west side of, the east side of that arc, I don't know which way the subduction is, but on one side or the other is the deepest trench in the ocean. The deepest point on our planet is the Marianas Island Trench. Okay, one side or the other of those islands, and that's exactly what you see forming here. Way, way deep. Lucas wasn't the director of the Star Wars. Was he George Lucas? Okay. I think he got to go down in one of the. Finally, they built a submersible submarine strong enough to go all the way down into the Marianas Trench. He wasn't the first to go down, but they let him go down just so he could see it because he had such a science fiction imagination. He got to go down and see it. You couldn't see much. It's so murky and so incredibly dark down there. You can only see where your little lights would shine. But the life forms that they saw there was just unbelievable. It made Star Wars seem tame. So, okay. Y'all are probably too young to So let's go to continent plate convergence. The less dense granite-type materials resist subduction. Who's going to go downhill? Neither one. They're both lightweight. They're not going to subduct. So the colliding plates pile up, producing a deformed, thicker crust of these lighter materials, and the Tibetan Plateau, Tibet, is just on the northern ridge of the Himalayas. So it's been lifted. That's the Tibetan Plateau. And then, of course, the Himalayas are what is forcing it up. The Himalayan mountains, these are examples of those continent conversion. Okay? The continental lithosphere comes into the other one, and they can't go down, so they have to go up. And makes for some pretty violent activity every now and then in there. Okay. Now, the third type boundary. We have divergent boundaries where the plates are moving apart, convergent boundaries where they're moving together. The third type, of course, is transform boundaries where they're moving past each other. Curve when two plates, they say slide past each other. That's not a very even slide, okay? It's a very rough slide, okay? It's like sliding on gravel, okay? You don't want to slide on gravel, okay? The crust is neither created nor destroyed in the process per se, but irregularities in the movement along the boundaries and the roughness and the discontinuities you have there create sudden jerks that produce earthquakes, okay? And you have the shaking of the earth. And one of the traditional ones of this is the San Andreas Fault. That's along the California coastline. Y'all have probably heard about that. That's right along here. In fact, if I understand the pictures well, this Gulf of California down here, I think is the southern edge of that San Andreas Fault. I don't know that for sure, but it sure looks like it to me. It comes closer to the coast up here and moves on up to the coast. And that's because some of these are sliding past. They're not converging or diverging, but transforming, moving past each other. Classic example of the San Andreas Fault. Now, I can't remember if it's this chapter or the next. I think it's the next chapter. There's just an incredible picture of where, along the San Andreas Fault, where there was an earthquake. We'll see it in a later chapter. I have been turning my pages very regularly. Let me go back and pick up some of this. On page 464, there was a blurb, a closer look on seismic tomography. It's a strange way to phrase it. A CAT scan of a person's body is a computer-assisted, I can't remember what, tomography, computer-assisted tomography. Diagnostic, and it puts together pictures of what's going on inside of you without them having to cut and see what's going on. Well, seismic waves can sometimes give us an idea of what's going on inside the earth without having to drill inside the earth. We couldn't do it anyway. So that's what that one's talking about. It's a pretty interesting read. I would definitely take advantage of that. And then there's also a blurb on measuring the plate movement. That's closer to where we're currently at. And that would be well worth your effort to take a look at that one. Blurb as well. Now, there's several examples here on a few pages here. One starts on page 467, talking about the distance between Natal on the easternmost point of Brazil and Mount Cameron in West Central Africa and talking about how they, if the average rate of spreading has been 2.5 centimeters per year. Now, a centimeter is about the thickness of your the width of your little fingernail. So that's 2 of them, and then add another half one over to the side. That's how far the plates are moving apart every year. Not incredibly far, okay? 2 little fingernails, okay, and a little bit more, okay? 2.5 little fingernails per year. Then they ask you to figure out how long did it take them to move apart if that's 5,000 kilometers. It's just an exercise in unit conversions. They think it's about 200 million years, okay? Been a while. There are some other examples here, and they're talking about distance from the trenches and earthquake depths. They're just giving you data, I guess are pretty accurate data, but asking you to calculate slopes and things like this, which seems like they're just kind of making up a problem for you to do, so I'm not going to get too much into that. Okay. So we're now on page 471. Oh, here comes a horde of people. Okay. Yeah, he went to get you, huh? Okay. So, Ethan's here, I was just about to say. And Keegan's here, but I've got to find her. There you are. Yes. Yeah, we're getting really close. We're about 10 minutes. Can you make it?
I can. That's what I was going to ask. Like, if we're not, I'm going to have to get the restroom.
Yeah.
It's
Yeah.
like 10 minutes, actually.
Yeah, about,
I don't want to, like, mess up because we'll get close to 3:15 too. So.
yeah, 3:15 is when we're going to stop this and go to the lab. Okay, so that's what I was trying to sort of figure out whether, yeah, it's probably worth it. Let's see what our present day understandings are. We probably won't get all this done, but we can at least start. The major remaining question is, why are they moving? Okay, what is driving the plate? Who's driving the plate? What's driving the plate? What's driving this motion? And there's, I think, probably 3 or 4 different hypotheses. Earlier text have focused on some. This one's working on another one, it seems like. This one's current working hypothesis is the convective cells in the asthenosphere. Remember, the asthenosphere is a hot, semi-liquid layer down there. And if you got heat coming from the core and through the mantle and stuff, and that's heating us up, it's just like putting a pot of water on the stove and turning on the heat, and after a while you see the water start convecting. The water in the middle is getting hot, coming up to the surface and going down along the edges. Can't remember if I asked this question before. Did any of your moms or grandmothers or someone have any of that visionware? It was actually glass pots and pans that you could see through. It's sort of an amber color, but you could still see. You remember that?
Yeah,
okay.
I know what you're talking about.
Okay. And when you watch water boil, you can see it do this kind of motion. That's convection. Rises in the middle and cools on the edge and goes back down. That's convection. Well, that's the idea here. In the asthenosphere, if you have some of these convective cells where it's rising up and then pulling the plates apart, that may be doing some of the driving. That's the one, convective cells in the asthenosphere. The hot fluid materials rise at the diverging boundaries, but you see, you have to have the diverging boundaries for it to rise. So what made the hot diverge in the first place? You know, that's where part of this hypothesis seems to fall apart. It rises at the diverging boundaries. Some escapes to form new crust, but the others drag it further apart. They come up, only some come up, the rest goes this way. The remainder spreads beneath the lithosphere, dragging the overlying plates with it. There's little supporting evidence in what made it diverge in the first place. Okay, who was Who's on first, or chicken or egg? Which came first? It's really hard to tell. Here's sort of a pictorial representation of that. This would be the rising, the convection of the magma from the asthenosphere. Now, they don't show the asthenosphere well here, but it's somewhere down here. This is coming up. A little bit of it breaks through and forms the crust on either side, but others of it moves outward, which sort of drags the plates further apart, which then makes it split more and more in. This is their idea, okay? Now, this book doesn't say too much about this, but another one says where these are being subducted, then gravity is pulling this plate down, and that may be what's pulling them apart. They call that slab drag, I think, okay, or something like that. But where that is happening, and these are subducting under, yeah, you have earthquakes could be going on here, but somewhere down here, things are getting hot enough that you get magma making its way, and if there's been little cracks and crevices formed here, either in continental plates or oceanic plates where they went below another one, then that's where you have your volcanic activities. These are on land. That would be like Mount Rainier or Shasta or Mount St. Helens, and, somewhere inland. The reason it's inland is because this activity is going on well beneath the plates here. Or over here, these are the island arcs, okay, that are forming along where this subduction happened, oceanic to oceanic, okay. And again, is this pulling down on this, forcing these further apart? All these are theories. They have very little supporting evidence. Okay. But this was the indication of the convection. Heat coming from the core, moving the magma up, and then cooling. So here is the convection going on. Center of your pot, the edges of your pot. And things are pulling things in that direction. Now this works really well two-dimensional. How does that work three-dimensionally? I don't know. Okay. And my goodness, we've got one more in before the break. Okay. Good to have you. Edward, right?
True.
Second? Yeah.
You get it.
Okay. All right. Okay. Is there one more? No. That is the last slide, but it's not quite the end of the chapter. I think we've got just a couple minutes. Mistakes, and misunderstanding. Here's one of the very best ones that I remember from, maybe not the best, but one. There was one time a theory, I think Barry Goldwater is the one who stated it. He was so upset with California. He was very, very conservative, California, very, very liberal. And he said, why doesn't California just break off and fall into the ocean? Okay. That's actually, some people have feared that. They think the San Andreas Fault, is it going to break off in part of California and fall into the ocean? No, that's not what happens with earthquakes. We're going to talk about this in a later chapter too. That's a transform boundary. It's just sliding past. There's no breaking. Hollywood is what has earthquakes opening up and people falling in. That just doesn't happen. If there is an opening up, magma's coming out. That's in the bottom of the oceans. There's no people falling in. So don't confuse Hollywood with reality. The person behind the science featured in this chapter was a good old naval officer, okay? Harry Hammond Hess, okay? Only lived about 63 years, but he was a U.S. geologist who played the key part in plate tectonic revolution. He was on the research vessels, naval research vessels, that went out and took soundings, they took cores, they compiled evidence. They interpreted evidence. He was incredible at doing what he did, and gathered much of the evidence for plate tectonic theory. Well worth a read. Remember, this can't be your source. This can be the idea for your paper, the source for the idea of the paper, but it can't be your source for the paper. You have to get that from somewhere else. Now, and I mentioned what they do in Iceland. Anywhere that the magma is anywhere close to the surface, you can sometimes harness geothermal energy, okay, from the earth to create other sources of energy. For instance, I keep wanting to say Battelle. I'm not sure that's the name of the power company out in the Pacific, on the Pacific Northwest. They harness heat from the earth, and they use that to make the steam to run the turbines to make the electricity with that. Very clean energy, by the way. Incredibly clean energy. Nothing's being burned, nothing's being destroyed. You're just harvesting that. Geothermal energy, good little Science and Society blurb there, more than half of a page. A few questions that follow that. It's well worth a read and a think. Okay. And I guess that brings us to the end. And as I always say, nothing replaces reading the chapter. So please read the chapters. I hope you read it before I talk about it, but if not, read it afterwards. Hopefully it'll make more sense. The summary here is one of the shortest summaries I can recall. There's a lot of several words that are italicized, and they show up in a very short list of key terms, so that's there too. But then applying the concepts, one of the longer list of these, 52 questions, multiple choice questions, great thing to study for the next test. So today, in just a few minutes, we're going to have the lab for chapter 17, followed by the last 30 minutes or whatever time you need for the test for chapter 17. So next time, we will start chapter 19, and we'll have the lab for 18, and then the test for 18, the one we just finished.
So that's on Thursday.
That will be Thursday, okay? So, another 2-hour lecture, 2-hour lab, and 30-minute test. That will be Thursday. So, after the conceptual questions, or applying the concepts, then there's 16 questions for thought, maybe a little shorter than most of the list have been, 4 for further analysis, that's about normal or short. Then they have some of the parallel exercises, which are more like the examples. We didn't do many of them, but some of those may be worth a look. There is an invitation to inquiry. If you find that interesting, you can take a look at that. But next time we'll start with Chapter 19, Building the Earth's Surface. Okay?
Building the Earth's surface.
Building the Earth's Surface. Follows from what we've been doing in this chapter, and then the next chapter after that is basically destroying the Earth's surface. It's not called that, but it's shaping the Earth's surface. And that will be the last of our chapters on geology. Then we'll move to meteorology and oceanography. But these are 2 fairly long chapters coming up, so it'll take a while. Okay, let's start verbally what we need to do. All right, I hope y'all have been reading the first page, okay, the second page, and the third page. All right, that describes what you're going to do. Now let me point out one little thing here, okay. What did I do with my glasses? Did I leave? No, here they are. Okay. All right. We're going back to minerals now. We hit rocks. We did minerals, then we did rocks, and now we're going back to minerals again. The fundamental building blocks of rocks are the minerals. And that's what we're going to be focusing on today. Now, the materials, we're going to do computer. We're not going to do what they say here about streak plate, magnifying glass, steel files, pocket knife, copper penny, anything else like this. Okay? We're going to use a computer program. Okay? Now, what computer program is that? I'm going to write it on the board for you. I don't have much room to write with the screen down like this. But I'll write it on the board for you where you go. I'll leave off the HTTP and that kind of stuff. You know how to get that. But the website is Web Mineral, written as one word, no S. There is another website called Web Minerals. Don't go there. Webmineral.com. And then what I have here is /data. I don't know if that's necessary or not. And to get to the very first one, you could actually do a /calcite. Okay? And from then on, you go from there. So that's where you go. Has everybody been able to log into a computer? Now, if you have a laptop, you can use your laptop. If you can log into this, do this one. But where you go is a website, webmineral.com, and then you can decide whether you do the /data or /calcite or whatever. I want everybody to get there and let me know if you've arrived. Okay? Now, while you're looking, let me go over a few more things here. What we're going to be doing in the lab today is you're going to look for color. So if you do go to calcite here and you find a table that says something like physical properties or properties of common minerals, see if you can find that. And in that table, you'll see color listed, and you'll see a whole string of colors probably. Streak, hardness. Hardness is based on the table that we have here. Okay? Cleavage and fracture, those are one column. Cleavage / fracture. Okay? Luster, density. Okay? Don't worry about other properties. But here's one thing I want you to point out. Want to point out to you. On page 331, there is one question. Was the purpose of the, well, two questions. Was the purpose of the lab accomplished? Why or why not? Just a 1 or 2 sentence answer will probably cover there. Anyone just come in that needs a lab? Or anyone who was here before that needs a lab? Everybody got a copy of the lab? Okay. You need one? No. Okay. That's data, D-A-T-A, not data. Okay. And you do /calcite if you want to. Yeah, scroll down, scroll down. Okay, keep scrolling. Oh, that's it. Yeah, okay, maybe a little bit. C. Okay. See calcite? There it is. All right. I don't think you need the /data or /calcite, but you find the table that says, okay, there's one that says general calcite information. Scroll down from there. Calcite images, scroll down from there. Calcite crystallography, go down. But then you see that next one, physical properties of calcite. Okay? Now, they're not in the same order that you have here, but you'll find just about everything you need there. If you go to page 332, and you see it goes across to 333, the first column says color. There's color, and you'll see several colors listed. You can write as many of those as you like. Usually the ones first are the most common, and then you write the others. Then luster is down next to the last. Fill in that. Streak, that will be the very bottom. Hardness is fourth from the bottom. Cleavage fracture. Cleavage is the top one, and fracture is the fifth one or so. So put down a little bit on cleavage, a little bit on fracture. Because they both need to fit in that same column. Now this sixth column here that says other. Cross out other and write density. Density. And you see in your table there, density, number 3 there. And it gives a number. Now, it's not actually a density, that's a specific gravity. If it had a unit after it, that would be a density. Without a unit, it's a specific gravity. So has everybody found the place? You had your hand up. Did you find what you needed? Okay. All right. Put it down so I can see what this is. Okay, just a second. All right, let's have a little bit of break here. Lady here is going to tell us a little bit about Miss Lawson State.
I hope you got some can.
Hey, how are y'all? My name is Shakaya Wyatt. I'm number 7 on the Miss Lawson State candidates list. Tomorrow, you guys will receive an email to your Lawson State account from Wednesday through Friday with all the candidates on the list. And we haven't really had a chance to talk to people in the Bessemer campus. So, my name is Shakaya Wyatt, and I hope you guys will vote for me. And Miss Lawson State is a representative for the school. So, yeah. I'm number 7 on the ballot, so y'all go ahead and vote for me.
All right, thank you.
Thank you.
Okay.
Hey guys, how y'all doing? So one of my lovely competitors already introduced herself. She's the great Shakaya White, but I am Victoria Barr, and I'm number 1 on your ballot, and I'm not strong. So my slogan is do not forget to vote because I like donuts. So I'm passing out little sweet things, and I think I'm the sweetest choice. So that's my thing. And I have a label, and my girl with me. Stand with Black Women. You've probably seen this flyer on the walls and stuff is what you do. I want you to know that you support it, and if not support it from each other, then definitely for me. So voting starts tomorrow. It comes into your email from the 11th to the 13th. So go in, click one of our names, hang out something, and know that have a good day.
All right, thank you. All right. Okay, is anyone still having problems getting to the site? Okay. When you get to webmineral.com, I think forget about /data and /calcite, webmineral.com. Look for something that says A to Z or something like that. Do you find that tab? Okay, click on that and then look for C index. Okay, click on that and you'll see a whole bunch of C's. Scroll down till you find calcite. You see calcite? Click on calcite and then you'll see, scroll down till you see physical properties. It'll be after mineralogical properties and others. You found it? There you'll see just about every one of those. What's that? Yeah, that's just because that's the first one here. Okay? And then you can do every one like that you just did. Now, let me say this before you get too bogged down with it. There are a few of these that you're not going to find a single mineral for. Okay? I think one of them might be feldspar. Feldspar is not a single mineral. So if you can't find something under feldspar, that may not be the one, but if you can't, then go out and type in feldspar somewhere and see what you can come up with. If you can come up with a mineral that is a feldspar, write that over feldspar here and then do your mineral based on that one. Because feldspar is a group of minerals, it's not one specific mineral. Okay? So there will be a few like that. It seems like maybe limonite might be like that. Bauxite might be like that. There's several that you might have to go and find a more specific name for a mineral than what they list here. And if you do, write that mineral name down and then fill out the table for that mineral. Okay? If you run into a problem, don't get frustrated. Get with a neighbor. This is a lab. You can work together. Or ask me and I'll see if I can help as well. Has everyone at least found calcite? Physical properties. If you haven't, please get in touch with me. Okay, you can pick one color or just list a couple of them. Just whatever you can fit in this block easily. You don't have to list them all, but just pick. Usually the first one's the predominant and then there's a few others. So, do like you. Makes sense. Okay. I'm on. Here to answer questions if you have them. I'm going to pause the recording until there's a question, and I'll try to remember to. Okay, this is a sample I brought from home this time. I don't know if this is an iron meteorite or not. You sure could convince me it was. You can tell it's sort of rounded like it has been melted, and you see sort of glaze to it, like it could have melted coming into the atmosphere. But you can feel of it. It's pretty dense, and you can see that. Now, I also picked up this. This is some gravel that was outside of our house in Georgia we had brought in. But this is a great example of cleavage planes. You can pass this around. You can see where the planes are very distinct. And they're not something someone's polished because you can see they're at different levels here. So that's a great example of several very clean cleavage planes. I'll pass this one around for y'all to look at. See the cleavage planes in that. Just pass them around the room. When you go out, you can look at this one. Feel of it. It feels dense to me. We'll do that in the next lab. another sample that we'll be using this one in the next lab as well. I'm pretty sure this is basalt. Now this has been polished on this side. When we redid our upstairs bathroom, the guy said, go get me some black granite, and that was back before I had enough sense to know there wasn't anything such as black granite, because if it's granite, it's light colored. So I went and they said, oh yeah, here's some black granite. I mentioned that to my niece, the one who got to go to Galapagos. She was in geology and geography. She said, there's no such thing. I said, what do you mean? And then later when I taught this course, I knew what she meant. This is probably basalt. And if you'll notice here, very fine particle size, very fine texture, okay? That would fit with basalt. Very dark color, that fits with basalt. I have 4 pieces of this. Please don't lose a piece because we're going to be using them next time, but I'll pass these around. These are the common, this is the polished side, sort of ignore the polished side, except you can see how small the particles, the crystal sizes are when you look at that. So I'll pass 2 of these in the front and 2 in the back, and when you finish with them, then please go back to me. Yes. What's that? It's basalt. Or in our house at the farm, we have large crystals, same color, large crystal, and that would be, oh my, what is that? I can't think of the name of it now, but it's the same thing, but large crystal size. It's slow.
So when I got black, I think I got all of that black.
Is it like this?
Yeah,
Or
I know,
is it
I've been doing it. I need to,
Yeah. No.
Oh, yeah.
Yeah. And no, it's not as large. I don't think so. I think
Uh-huh. Yeah. 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 Okay. I got black granite, I got stuff here. Yeah. Wow.
most of you have already done calcite, but if you want to see a calcite crystal, this is one of the prettiest calcite crystals. So I'm going to pass this one around. See if that seems to fit what you were just studying. I've got one other here that will do pretty well too. I'll pass it down this side. I'm not going to do the others because these were brought to me by one of my students who actually worked in a coal mine. And he said, yeah, calcite crystals grow near coal, and there's the coal on that end and the calcite on that end. So he brought me some, and boy, some of these crystals are just unbelievably beautiful. A couple of them are broken off, but I don't want to mess up. I'm already messing up before some. So I'm going to put these out on the table, and you can look at the rest of them out there. Now, we haven't talked about this particular type of thing, and this one broke. I'm sorry about that. This is a sample of what they call a geode. From the outside, it just looks like an old rock, but when you slice it, you see it has all these layers in it. And that's formed by a chemical process by which the center does one thing, and then the chemicals are attracted to different methods. These are both sort of bluish. There's a couple of different ones in here. But you see the rings, almost like the rings of Saturn, okay? But these are geodes. I wish I had one that wasn't broken. I think I'll find one in a minute. It's not. But these will be out on the table on the bag. It's not anything we've talked about in class. You'd have to take a more extensive geology course to probably find out more about that. Yeah. Elsewhere. Okay. Elsewhere, okay. 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 Oh yeah, Labradorite would be perfectly fine. Okay. So write that Oberfeldspar here. If you can find the stuff, I'm waiting until you see if you do. Yeah, go under your L and see if you can find Labradorite. There it is. Sure. So right, Labradorite. Yeah, that's the one she chose. Okay, I found the thing. Looks just like a rock. A little unusual. It looks sort of like an egg. But then somebody had broken it at some point, and when it breaks, you can see the inside are those layers. This is a really ugly kind of a geode, but it's a geode. Different stuff in the middle than what's on the outside than what's on the outside of it. The geochemical way it was formed the different minerals on the outside of it. So it's just interesting. I don't know exactly how they're formed. I just know it's a geochemical process. It attracts something in the center and then varies as it grows outward. That's an example of a geode in the wall. Anytime you have a question, ask me a question. Don't let me go on. place here in Bessemer, it used to be, where we got our countertops when we redid our kitchen. And I went there, something to do with that, and found all these little scrap pieces there. I said, hey, can I get some of these samples? He said, sure. He just handed me bunches of them. Here's an example of what he called was Indiana limestone. Can anyone tell me what kind of rock, this is a rock now, not a mineral, what kind of rock limestone is? Sedimentary rock. What kind of sedimentary rock? Chemical sedimentary rock. Now, if that undergoes some metamorphosis, what does it become? A lot of heat, a lot of pressure, a lot of time, it becomes marble. Much harder, doesn't flake off the way limestone would. It will get eaten by chemical, but much more slowly. This is a cream marble from Italy. This is a catic gold or something like that, also from Italy. Two different types of marble. Now, I've never heard a definition for this, but I've heard people talk about travertine, which also comes from Italy. And what it looks like to me, that's something in between a limestone, but not quite a marble yet. So maybe a partially metamorphosized limestone, but it just isn't as hard and as together as marble is, but it seems to be a little bit better than limestone. So these will be out here on the table. What's that? Yes, exactly. Yeah, pretty. It's a pretty texture too. It's really great. Reminds me of marble, but it's not quite as hard. Okay. Most of the countertops most people want are what? Granite. That's very common, especially, well, it's the most common rock in which crust? Which type of crust has more granite in it? What? Yeah. There's two types. One's underwater, one's above water. Above water, the continental crust, mostly granite, and if this is a piece typical in the color, light colored, though it has some dark in it because it'll always have something. Remember, it's a rock, not a mineral. It has many minerals there. Now this is the polished side, here's the unpolished side, but you'll see, especially on the breaking side, that the crystals are fairly good size, fairly large crystal. Now here's a bit darker granite, but this is still granite. This one you can definitely see larger crystal size, but there's a lot more plagiate clays and orthoclays, that kind of stuff in here, a lot less silica because of the darker color, the browns. Yes? What's that? Food safe? Oh, absolutely, yeah. It's really hard to break down these minerals. Okay.
I mean, they won't impact your food.
What's that?
The minerals don't impact your food.
No, no. I would say aluminum pot would have closer impact your food than a mineral would. Now, if it's something very porous, the mineral could trap bacteria and stuff in it, and that could affect food, but the mineral itself probably wouldn't. Now, looking at the surface of this one, I'd be hard-pressed to call that a granite because it's so dark. But if you look at the edges and stuff, it's not quite as dark, just a lot of those browns. This is they call it a granite, but they may call lots of things granite that really aren't. But I wish I could remember the name of our counter. Gabbro. Gabbro. Gabbro is a large crystal, black, and if you have large crystal rather than fine crystal, that's probably gabbro. And it's also very hard, very strong. Okay. This is bordering on probably gabbro. It's probably still classified as granite, but just barely. It's everything's an integrate. Okay. So I'll put these granites out of each other too. Should have brought this in with the first one because the first one was mostly white. I said it's largely quartz. You can see the crystals in it. This one you can't see the crystals as well. Only a couple places you can see them poking out, but this is more what they would call a pink quartz, just caused by a few impurities. But guess what? Color is not the best indicator, because most of these are white, and then you see all those other colors there. They can be a variety of colors. That streak, almost always one single color. That's a much better indicator of the mineral than color. So this I'll put with the other quartz-like material. You would have to rub it on pretty hard sandpaper type stuff. Yeah. I don't have any of that. One more little piece of the salt somewhere out there. These are two samples of sandstone. If you rub your hand across them, you'll feel the grittiness and know it's sandstone. What kind of rock is sandstone? Say again? Sedimentary, for sure. Which kind of sedimentary? Second? No, chemical is limestone. Plastic, meaning particles, the sand particles. Now, if you were to rub your hand over this one, you'll actually get the sand coming off in your hand. That's why I don't want to pass this around. It'll get all the desk dirty. So what would be the difference in these? This you can rub to your heart's content and it's probably not going to come off. Probably what was different in these two? The second? It could have been, but more likely, yeah, the pressure. Remember the two phases of lithification, how it became a rock? There's that other word, lith, in it. Two stages. One had to do with pressure, the C word. Second? Compaction. And then the other was cementation. Either this got compacted a lot better or else the cementing agents are much better. This one may be a combination of both. It's losing fast. Okay, it leaves little particles all over in my bag. So these are sandstone. Finally, I have a whole series of things. These would be clean enough to leave in here. I took my table out, so I'll put them out. They have little numbers on most of them with a key here, and you can actually see some of the minerals you've been looking at in your table. At one time, they were in some order, but they've been viewed so many times they're in no specific order at all now, or some of them are. So I'll leave these on the table, too, with your handout, with the thing. Some of these are hard to get out of the thing, but I did want to show you this one, but I can't get it out easily. Some of these are fairly fragile, so be gentle with them. This is number 23, and 23 is mica, a variation of muscovite. And if you remember, mica comes off in sheets, two-dimensional crystals. Look at that cleavage. Really strong cleavage here and here, and not so much on the edges. Fractures here, cleaves there. Comes off in sheets. That's number 23. We tilt it up like that so it's easier to get hold of. If you are missing, I don't know why. They may have fallen into some other thing. But I'll put this outside for you to look at as well. I'll run down and rinse my hands off. I'll be right back. Any questions? You got one? That's fine. I'll let you. Yeah. You can put numbers. Now remember, the other is density. Everybody getting density? That last column. The last column, remember, the other is density. Density. Got to go back through them. That's one of the most important ones.
No, I didn't. I gotta go all the way back. Yeah. I even put on the right. Roll with something like that. Would you like us to turn them in?
Yeah, if you're through, you can turn them in. And if you want to, you can get started on your test whenever you would care to. Good deal. Good deal. Ready for the test?
Yes.
Okay. Let me remind you before you go, everybody answer the question on page 331. Bottom of the page? Good. Okay. So let me find the test. Okay, I'm going to pause the recording.